Hello ladies and gents, this is Daniel for Rock the JVM, and this video is about the free monad in Scala. Now, this video will be quite advanced, so this will require you to be an advanced Scala user, and if you have some knowledge about monads and some knowledge about cats, the library in the Scala ecosystem, that will be a bonus, but I'm going to give you all the necessary prerequisites in this video. As always, I'll recommend that you code with me in this video to make sure that you solidify all the concepts that I'm going to show you here, and whenever you need to refresh your memory about them, just refer back to this video or to the written form at the blog as usual. Alright, so here's the deal. I'm going to create a simple object in my application here in my project in IntelliJ, and I'm going to have a small main method in case we need to test some stuff, and we will test some stuff by the end of this video. Now, what is the free monad? You probably know about monads in Scala already. I have a bunch of videos here on the Rock the JVM channel describing monads in a couple of different angles. And monads are essentially data structures with sequential capabilities. So the ability to write sequential computations is abstracted away in the monad concept. Now, the free monad abstracts that a little bit differently. So you probably know about lists, options, tries, and many other data structures that are monadic. And the fundamental operations of monads are pure, that is the ability to wrap a value into a monad of that value, and the ability to flat map. And flat map takes a function from A to an M of B, and this returns an M of B, and you're probably well aware of list.flatmap, for instance. Now, in cats and in other Scala functional programming libraries, there is a trait called monad, which abstracts away this higher kind of type. We usually call that F or M if you like the monad name better. And this has the method called pure that wraps a value of type A. So A is of type A, and this returns an M of A. And the second function is flatmap. And this takes two type arguments A and B. It starts with a monad of A, so M of A, and a function that turns an A into an M of B, and this returns an M of B. Now, if you know cats, this is second nature to you. So monad takes a higher kind of type M, and so on and so forth. And for the regular data types such as list, option, and so on and so forth, we have implicit type class instances of type monad for list, option, and so on and so forth in scope. Now, the free monad looks a little bit different. I'm going to define that as a trait. I'm going to call this free. And this takes two type arguments. First of all, the M, which exhibits the monadic structure, and the type argument A, which is the value that this M is going to be associated with. So notice that the type argument A is distinct from the type argument M, which is the monadic structure, and the value type contained in that monadic structure. So we separated the two in this free data type. And the pure and flat map look a little bit different. So pure looks something like this, that wraps a value of type A, and this returns a free of M and A. And the flat map method takes a type argument B, because the type argument A is already denoted in the header of the trait. And the function takes a value of type A, and this returns a free of M and B. And the final return value of the function is going to be a free of M and B. So notice that the structure is a little bit different, but the concepts are the same. Now, we can also argue that the pure method needs to not depend on a specific instance of free, but rather have the pure method inside some companion object, because it makes no sense to run a pure on an existing free and obtaining a new instance of free. So I'm going to wrap that in an object. I'm going to call this free, and I'm going to move the pure concept in the free companion object, and I'm going to add the appropriate type arguments, so M and A, and this will return a free of M and A. For now, I'm going to leave this unimplemented, and we have the pure capability inside the companion object and flat map inside the trait, so that we can transform an existing instance of free into another instance of free. And because we have pure and flat map, much like the regular monad data type, we can also implement the map method for free. So we can add a map method with a type argument B and a function that turns an A into a B, and this will return a free of M and B. And if you know the regular cats data types, you know that this can be implemented in terms of pure and flat map. So I'm going to implement that as flat map. Considering a value of type A, I'm going to return a pure FA. And the pure needs to be imported from the object free. So I'm going to import free everything. Notice that I'm using Scala 3 in this video. You can also use the underscore syntax if you like Scala 2. Everything that I'm going to talk about in this video is applicable for both Scala 2 and Scala 3. I'm simply going to write Scala 3 in this video. All right, cool. So we have pure and flat map, and we have the map method for free. Now, another function that's very important for the free monad is called lift. And it's usually named either lift, exactly like this, or lift m, or lift f, something like that. And I'm going to use lift m here because I've used the m name for the higher kind of type. And this wraps or turns an ma, so an m of a, into a free. So free with m and a. So this destructures the monadic type m of a into a free with the type constructor m and the value type a. Right now I'm going to leave this unimplemented because I'm going to start describing why we need this free monad in the first place, and then we're going to implement all these functions and describe all the features of the free monad itself, because that's probably going to take a lot of time. And I know for a fact that you need a solid motivation why we need the free monad in the first place so that you can watch until the end of the video. So, why do we need the free monad? Well, we need the free monad for a very similar reason why we need the monadic thing in the first place. And that is to say that we want to sequence computations. So that's the reason why we need the monad data type. But the reason why we need the free monad is to be able to sequence computations in abstracto. So sequence computations as data structures, and then attach the monadic type at the end. I'm going to give you an example. Let's assume that you're interacting with some sort of database. I'm going to define the operations that you can perform on that database as a trait. I'm going to call this dbops that take a type argument a. So you can read and write values in this database of this type. And I'm going to define some case classes, and I'm going to define the standard CRUD operations. So create, that takes a type argument a, and you'll have a key, let's say it's a string, and a value as an a that you want to insert in this database, and this extends dbops of type unit because you don't really need to return anything from the database. It just performs an effective type unit. And let's say a case class of, let's call this read, with another type argument a, which reads a value of type a with under the key, which is a string, and this extends dbops of type a. This time you're reading a value a from the database. Let's create a case class, let's call this update, that again takes a type argument, a key is a string, and a value of type a, and this extends dbops of type a. Let's assume that you want to return the old value before the update, and a case class called delete, and this doesn't take any type argument. Let's say key as a string, and this extends dbops of type boolean or unit. So we've defined all the operations here in this database. If you define operations like this, it means that you've defined a so-called algebra. And this algebra describes all the operations that you want to perform. So we have create, read, update, and delete. Now, depending on what you really want to do in real life, this algebra may contain data structures that reference other data structures. So in the end, if you want to perform an operation, you may actually perform an entire tree of operations in your application. So I'm going to keep the algebra quite simple with the standard create, read, update, and delete operations in the database. Now, I'm going to add some definitions, and I'm going to define a type. I'm going to call this dbmonad, which is a monadic data type that describe operations under the free monad. So I'm going to take this dbmonad of type A as a free, where the monadic data type is dbops. So dbops itself, not dbops of int, string, whatever. And the type argument a that I've defined this with in the first place. So db monad is a free monad where the db ops is the actual operation that I want to perform. Now the db ops, as you can imagine, these are just data structures. So I can combine these data structures to contain some sort of program or to describe the operations that I want to perform on a database, and then I'm going to transform this into something that produces an actual effect. But bear with me here. So right now I've defined my data structures, and this very fancy type, I'm going to call this db monad. Now, I'm going to implement instances of this db monad for every single operation in my algebra. So I'm going to run some sort of smart constructors for db monad. So I'm going to create 4 methods: create, read, update, and delete, that mimic these data structures very well. So I'm going to have my create, which takes a type argument a key as a string, and a value of type a. And this returns a db monad of unit. So db monad of unit. And because I need to turn a db ops of unit into a free, I can use this liftm function that I've just defined to do just that. So I'm going to say free.liftm with db ops and unit in between square brackets, because these are the types. And I'm going to wrap one of these data structures. So I'm going to write a create with key and value. So notice that I've wrapped a dbops unit into a free of dbops and unit. Now, this free data type will give us some additional properties that will allow us to compose these operations very nicely. So bear with me here. I'm going to create smart constructors for all these data types. So I'm going to have a get method that takes a type argument a under a key, which is a string. So I'm mimicking the structure of dbops as well. So this is a db monad of type a. And I'm going to use the same technique. So free.liftm, and I'm going to have db ops and a, and I'm going to wrap, so not square, okay, just that. And I'm going to have a read under this particular key with the type argument a. Cool. And I'm going to do similar thing, update with a type argument a key, which is a string, and a value of type a. This returns a db monad of type a. Same thing, so I'm going to say free.liftm with the types db ops and a, and I'm going to create an update data structure that takes type argument a, and I'm going to have my key and value. And finally, I'm going to have a delete thing, so delete with key as a string, and this returns a db monad of type unit, and I'm going to run the same technique, so free.liftm with a delete under this key. So notice that I've created some smart constructors for this db monad kind of thing, which wraps a db op. So now we have the algebra, we have, let's call this fancier algebra. Now with this fancier algebra, I can actually describe some computations that I might want to perform on a real database. So I'm going to define my little program that I might want to perform on an actual database. So this is going to be, let's say, a db monad of type unit. And I'm going to run 4 comprehensions because my free monads are decorated with flat map and map, so I can run a 4 comprehension. And let's assume that in my little database, I'm going to say create under the type string. Let's say the key is 1, 2, 3, 4, 5, 6, and the value that I'm going to post inside this database is Daniel. And I'm going to try to fetch the name as a get under the value string under this key 1, 2, 3, 4, 5, 6. So I should be able to retrieve the value Daniel from the database that I'm going to identify later. And let's say I want to create something else. So create string with, let's say, 5, 6, 7, and then I'm going to have my name.to uppercase, because this name was fetched from the database, so it's supposed to be a string. And let's say that I'm then going to delete the key 1, 2, 3, 4, 5, 6 earlier. So we have 1, 2, 3, 4, 5, 6 deleted, and I'm going to yield unit because I don't really care about the return value. Delete returns unit anyway. So this is going to be a DB monad unit obtained by composing other DB monads inside this for comprehension. So this for comprehension is a sequence of operations. So notice that we're now using the monadic structure of free to be able to sequence all these computations together and describe a full program that writes or reads things from the fictitious database. So if I really want to create the value Daniel at this key 1, 2, 3, 4, 5, 6, get the name, write it to uppercase and associate it to some other key, and then delete the original key in a real database, I might want to describe this little program under the monad DB monad, and then I might want to evaluate that, because right now this is just a data structure that describes a computation that's not a real computation. So this is a description of a computation. Now, if we want to actually run the little program, we need to evaluate the program. And we need some sort of interpreter or compiler of the program to be able to walk through all the data structures that are involved in this program. The program might be quite complex, and to be able to produce a real-life effect out of it. Now, in order to be able to evaluate this program, we need some other data type that will be able to produce some real effects in the real world after evaluating this program. And a good candidate for that is the I/O data type from Cat's Effect, or from other libraries such as Zio. So I will define a very, very simple I/O data type that's very similar to what Cat's Effect offers. I'm going to define a case class. I'm going to call this I/O that takes type argument A, and this has a method called unsafe run, or simply called run, that is a zero function that evaluates to A. This is also called thunk for historical reasons. But I'm going to call this unsafe run because it's clear. And I'm going to define an object IO to be able to create instances of this IO data type on a particular value. I'm going to call this apply, or create actually, because if I name this apply, this will come into conflict with the apply defined by the case class. So create with a type argument A and a value that is a by name expression that evaluates to A, and this returns an IOA, and this will be an IO with a zero function that evaluates to that particular value. Right, so I'm going to simply create this data type, and I'm going to try to transform this DB monad unit into an IO unit such that after we transform the DB monad unit into an IO unit, we can call the unsafe run method and actually produce all the effects described by this little program. So this, my little program here, is our business logic, so to speak. This is the thing that we care about, but we also need something that will actually produce the effects described by this little program, and an IO is a good candidate for that. As I'm going to show you shortly, the free monad allows us to use any sort of data structure that will produce any sort of effect in real life. I'm just picking IO, but given by the structure of the free monad, we can replace IO by any other kind of structure. Now, to that end, we will need a function in the free monad that's called fold map. And fold map will belong to the free trait and will have a signature that looks something like this. I'm going to call this fold map. And this will have another type argument G, which is itself generic, because we want to turn this M thing into G's, that is DB ops in the style that we wrote earlier, into IOs that we can then evaluate. So this will be a G, and I will require this G to exhibit monadic structure. That is, we need a given monad G in scope, or an implicit monad G in scope if you're using Scala 2. And we will need some sort of natural transformation from M's to G's. And this natural transformation will be of type, and I'm going to define that as a trait. So trait, I'm going to call this nat trans. This will take two type arguments f and g, both of which are themselves generic. And nat trans will have an apply method that, given a value of type fa, this will turn an fa into a ga. For instance, if you want a list into an option, or an option into a try, or a try into a future, or things of that nature, natural transformations are your way to go. And natural transformations are a concept that I've used in my little demonstration for why monads are actually monoids in the category of endofunctors. The infamous phrasing and category theory. And traditionally, this, rather in the CATS library, this natural transformation is represented by this very cute squiggly arrow between F and G. So this natural transformation will be a transformation between the original M data type, which in my original program was dbops, and the new G data type, which is in my case IO, the thing that I've just defined a couple of seconds ago. So this nat trans will be from M to G. And this will finally evaluate this free monad into a G of A. So I basically collapse this free monad under this natural transformation into a final G of A. In my case, this will be an IO of A for my little program, which has this unsafe run method, and then it will actually start performing all the computations. So the idea here is to keep the little program that I've written a couple of minutes ago fixed. So this business logic will be fixed. So business logic is fixed. But rather, the evaluation or interpretation of this business logic can vary or can be changed later. So the little program is very important and needs to be fixed, but the evaluation of that can be changed. This is why the free monad is such a useful tool. And this can only be performed under the presence of the fold map method of the free monad. So if we can perform, or if we can create a natural transformation between the dbops, the abstract algebra for create, read, update, and delete, the abstract data types, into actual effects that will perform something in real life, then we can evaluate the little program under fold map. So let's perform a natural transformation between dbops and IO. So I'm going to create a little value or method. Let's call this dbops to IO. Actually going to call that a val. And this will be a natural transformation instance from dbops to IO, the little squiggly arrow. So I'm going to have a new this thing, so dbops to IO, and I need the apply method. So the apply method will take a dbops A, and this will return an IO A. Now, because dbops is just a data structure having a few options here, create, read, update, delete, I can run an actual pattern match. So I'm going to say fa match, and in case we get a create with a key and a value, then I will create an IO, which will perform something important here. So I'm going to have an IO.create, and here I'm going to have the actual code that uses the database. So here is where you can actually start fetching the database connection and actually performing some insertions or what have you. I'm going to simulate that by printing something to the console. So print line, I'm going to say insert into people. This is, let's say, the table where we have the key and values. Let's say ID and name, values, and inside the tuple, I'm going to inject the key and the value in an s-interpolated string. So this will be the SQL statement that will actually be performed in the database. I'm actually going to print it to the console because I don't have a database to show you. And let's say that I actually have an in-memory database as a map. So I'm going to say val my database as, let's say, a mutable.map. And I need to import the mutable package. So I'm going to import Scala collection mutable for string and string, and I'm going to have new mutable.map. Actually going to use the apply method, and I'm going to say my db plus equals, and I'm going to associate the key to the value. So I'm actually going to insert something in my little database. Now, the value here is of the generic type A, and I have my map as a string and string. So let's create some functions to serialize and deserialize general values to strings. So I'm going to have, let's navigate above, I'm going to have, let's call this serialize a value of type A into a string. And in real life, this will actually be performed through some sort of serializer, like a JSON serializer or what have you. I'm going to simply say value.toString, and a deserialization, so deserialize, that takes a value of type string. So have string, and this turns a string into an A. Of course, you would use an actual deserializer in real life. I'm going to simply convert that value as instance of A, which is absolutely abhorrent, but I'm only going to operate with strings here for this little demonstration. So I'm going to add some to-dos here, replace these with some real serialization. And assuming that this is my actual serializer, I'm going to say serialize with value. And then I'm going to return unit because this create thing is a dbops unit, if you remember the definition. So I need to turn that into an IO unit, which means that I need to return the unit value at the end of the IO creation. Cool, let's add the other cases. So in case we get a read under a key, I'm going to say io.create, and I'm going to say print line select star from persons, or from what I call it people. So people where ID equals the little key. So I'm going to use it as that. I'm going to say limit 1 because I only need to return a single entry, and I'm going to return my DB associated to that particular key. I'm going to say my DB invoked on the key, and because this is a string, I need to turn that into an actual value A. So I'm going to say deserialize for DB key. And similarly for the other operations, I'm going to have a case for update with key and value. I'm going to say io.create, and I'm going to print line, say update persons, or call it people. Why do I call it persons? Name equals, let's say, value, where ID equals key. I'm not even sure if this is correct SQL, but I think you get the idea. And I'm going to say old value as my DB invoked on the key because I need to return the old value, so I need to save it first. Then I need to make the new association, so my DB plus equals, and then I'm going to say key associated to the new value. And then I'm going to return the old value as the right type A, so I'm going to deserialize that. So I'm going to say deserialize old value. And finally, of course, I need to serialize this value thing. So I'm going to say serialize on value. And in case we get a delete on a key, I'm going to say io.create, and I'm going to simply say print line delete from people where ID equals whatever key. And I'm going to return unit because delete is a dbops unit, so I need to return an IO unit instead. So this is the structure. This is the logic by which we're going to evaluate my little business logic through the fold map function. So if I have something like that, I can then evaluate that program by simply saying, let's call this IO program, as my little program, which is the business logic, which I called it fixed. Then I'm going to call fold map on that. And I need a natural transformation between dbops and IO, which I already have here. So I'm going to say dbops to IO, and this will be an IO unit. Now, this is only possible if I have an implicit or a given value of type monad IO. So I require fold map that the new type G, which is in my case IO, be a monad through type bound here. So I need to create an IO monad. So I'm going to navigate to IO, and I'm going to write an implicit val or a given instance. So I'm going to say IO monad, which is a monad of type IO with, and I'm going to define my pure method, which wraps a value of type A. So I'm going to say IO with the unsafe run evaluating to that particular value, and the flat map is going to be a new IO, where the unsafe run method is going to be a 0 function that will evaluate f on the unsafe run of ma. So I'm going to say ma.unsaferun and wrap that into an f. So this is going to be an f of IOA, and then I'm going to call unsafe run again. So the IO that I'm going to return after this flat map is going to take a 0 function. It's going to force the evaluation of the original monad, run the f function on the resulting value, which is an IOB, and then call unsafe run on that because I need to return a simple value of type B. So let's follow the types here so that we have this a little clearer. So from here to here, we have a simple value of type A. So ma.unsaferun returns a value of type A. Then we're going to have from here to here, so f of A, this is going to return an IOB per the definition of f. And then I'm going to call unsafe run here because the final value from the beginning to the end needs to be of type B, which is what the 0 function requires of the new IO type. So I hope this is clear now. And given the fact that I have a given IO monad, of course you can implement that with implicit values if you are writing Scala 2. Notice that now my little program foldmap with dbops to IO now compiles. So if I compile the entire code, notice that the code compiles, and I can then run in main. I'm going to say IO program.unsafe run. And this is the final bit where the program will actually perform some real-life work. So this performs the actual work here because we've already defined how the transformation between dbops and an actual effect is supposed to take place. And this is the crux of it. This is how we can transform an abstract program into a concrete program through the natural transformation. Now, the beauty of using the free monad is that the exact same business logic which we deem to be fixed can be evaluated differently, or it can change the interpreter or the evaluator of the program if you can supply any kind of natural transformation between dbops and some other data structure that is important to you. Maybe you want to turn the dbops into something that performs asynchronous work or synchronous work, or option or list, or if you want to aggregate the results, or any kind of data structure that you think is appropriate to evaluate this program under your own restrictions. This will be possible under the free monad. So this interpretation, or rather this separation between the abstract program and the evaluation of it, is very similar to the tagless final approach, which I also demonstrated in another video here on the Rock the JVM channel. But back to the actual performance of the work. Right now, if I run the application, we'll get some non-implemented errors because we have some to-dos left. So we have pure, lift m, and we have some functions from the free trait. So let's go implement those real quick. Now, in order to be able to build pure instances, we need some classes that extend this trait because right now we don't have any instances. So I'm going to define a case class. I'm going to call this pure, which takes a type argument m, which is itself generic, and a value a, and this will have an a, which is an a, and this extends free with m and a. Now, don't worry about the compiler errors. Pure needs to be abstract because it has a bunch of unimplemented methods, but I'm going to implement all of them in the free trait. And with the pure data type, we can also implement the pure method, which is, of course, simply an instance of pure, so pure a. And I'm going to add a case class for flatmap. So flatmap takes the type argument m, which is generic, and two value type arguments a and b, and this will have a free a, so free with m and a, and a function that turns an a into a free with m and b in this case, and this extends free with m and b. And of course, with flatmap here in the trait, we can actually go ahead and implement that real quick. So I'm going to have a flatmap with fa, which is this, and the transformation function f. All right, cool. Now, both of these need to have the foldmap method implemented, which we can implement right in the case class definitions, or we can implement that in the trait via pattern matching. We can choose either way. So I'm going to aggregate all the logic here under the foldmap method in the trait with pattern matching. So I'm going to say this match, and in case we get a pure a, And per the definition of fold map, I need to create a GA out of this little value here, A. Now, because G is a monad, I can obviously use the pure method here. So I'm going to say monad G dot pure with the value A. Now, I cannot really say monad G dot pure A because I don't have any kind of implicitly for monad. So I'm going to create a companion object for monad, and I'm going to define my little apply method that, given a type argument m, will fetch whatever implicit there is for monad m in scope. So I'm going to use a using clause. If you're writing Scala 2, you can use an implicit keyword. So I'm going to say using monad, which is monad m. And this is going to be a monad m, which is monad. So this will be with a capital M, and I'm going to simply surface out whatever monad is implicit in this scope. So notice that I can say monad G.pure A to create a GA out of a simple value. And in case I get a flat map with FA and F, I will need to then use this natural transformation. So here's what I'm going to do. First of all, I'm going to say FA fold map with the natural transformation. So FA fold map natural transformation will return a GA. So right now we have a G of A, but I need a GB. Now, how can I turn GA into a GB where G is a monad? So obviously I'm going to invoke monad G's flat map method. So I'm going to say monad G, then flat map, and I'm going to start with this GA. So right now I'm going to have a GA in between these parentheses. And I need a transformation between a GA and a GB. So this is going to be from an A to a GB. So I'm going to have f of A. Now, this is a little bit harder to follow because FA is a function from flatmap's definition, and the function f takes a value of type A and returns a free MB. So this little expression is a free MB. So I'm going to follow the types here, and I'm going to say free MB here. And I'm going to isolate that so that you can see it more clearly. So free MB. This expression is a free MB. Now I need to turn that into a GB, and I can turn that into a GB by calling fold map again. So I can say dot fold map with the natural transformation. So this expression over here is a GB. So our giant flat map takes a GA. So this is a GA. And the function takes an A and returns this little thing, or rather this big thing, which is a G of B. So this is a valid application of flat map, and this can implement fold map on this little data structure. And now we only have lift m to implement, and we're going to implement lift m by not forcing the evaluation of m because we don't really know what m is. So we're going to create another case class. We're going to call this suspend or defer or something like that. And suspend takes a type argument m, which is of course generic, and a value of type A, and this will have an MA, which is a wrapper already, and this extends free with M and A. Of course, we now have to add a new case for the pattern match. So in case we get a suspend with MA, then we're going to simply apply the natural transformation on MA and return a GA. So this will be a natural transformation dot apply on MA, because natural transformation turns an MA into a GA. And that is it. This is the implementation of fold map for all our cases here. That was a little bit tough to follow. I hope I made this easier through following the types here in the comments. And this lift m will now implement a suspend. So suspend with MA, and we have all our code implemented, and we can actually run our little program. So I can actually start compiling this little code and running into the console, and notice that all my SQL statements were executed, that is, they're printed to the console. So the free monad has the beauty that you can fix your business logic, but you can vary the interpretation of that business logic for whatever use case you need. All right, folks, there you go. A tough video on the free monad in Scala. I hope you found it valuable. If you did, go ahead and click the like button for me and subscribe to the Rock the JVM channel for more videos like this. Check me out on Twitter and LinkedIn. I post fresh updates on upcoming material. And check out the Rock the JVM website and blog. I have hundreds of hours literally on everything in the Scala ecosystem, including the Scala language, magic about the Scala language, cats effect, Spark, Akka, Flink, and everything in between. Until next time, I'm Daniel, signing off.